Hello friends, welcome to this session. In the previous session, we have discussed IES solutions for the topic network elements. Friends, for gate exams point of view or for APGenco or APTransco point of view, this theorems part is very important and you may expect at least 2 to 3 questions in this network theorems in APGenco and APTransco. Friends, let's start our discussion. In this session, we are going to discuss all the 10 theorems in our electrical circuits and important problems in electrical circuits based on these theorems here. Our first theorem is source transformation theorem, and next we will discuss superposition theorem, Thevenin's theorem, Norton's theorem, maximum power transfer theorem, reciprocity theorem, intelligence theorem, Millman's theorem, compensation theorem, and substitution theorems. So let's start our discussion. So first is source transformation theorem. In this theorem, any practical voltage source with a series resistance or current source with a parallel resistance can be transformed into a current source with a parallel resistance or voltage source in series with a resistance respectively. That means, friends, in any network, if you have a voltage source in series with the resistance, it can be represented as a parallel current source in parallel with the resistance. That means a voltage source is having in series with the resistance can be represented as a current source in parallel with resistance. And in order to convert from voltage source into current source, we are going to use Ohm's law here. So let's take an example here to understand this concept. If RD is equal to 0, find ID here. That means if RD is the resistance of the diode is 0, we need to find here the value of ID here. Okay. So in order to solve this, we are going to use a technique of source transformation. In the source transformation technique, so what we will do is we will transform this voltage source in series with the resistance into a current source in parallel with the resistance. So if you observe here, I have transformed here. So 10 volts in series to 2 ohms can be represented as 5 amps in parallel with 2 ohms here. So I is equal to V by R, that is 10 by 2 is nothing but 5 amps, and 5 amps are represented here. Now if you observe here, we have 2 ohms in parallel with 2 ohms here. So equivalent is going to be 1 ohm here. So I have represented 1 ohm here, and ID is a current flowing through the diode we need to find here. So this is the equivalent circuit right now here. Now next here, current source in parallel with the resistance can be represented as a voltage source in series with the resistance, where V is equal to I into R. So 5 into 1 is nothing but we will get 5 volts, and series with the 1 ohm resistance and ID here, and I am converting this current source in parallel with the resistance into voltage source in series with the resistance here. So this is the equivalent circuit. So by applying KVL here, so minus 5 plus 1 into ID plus 1 into ID plus 3 V is equal to 0, we will get ID is equal to 1 amp. So next, friends, so here we need to find the Ix value. Okay, you can use any other techniques such as nodal techniques, mesh analysis, you can use here. So here we are going to use a source transformation here. So important thing is 10 volts in series of resistance. Here Ix we need to find. So here the target terminal is Ix across Ix flowing through the 1 ohm resistance. So we are not going to apply source transformation where we are having targets. That is Ix a target here. Okay, and depends upon this Ix value, we have 2 into Ix is a current source. That is, it is a current dependent current source here. So we can apply the source transformation technique for dependent sources. So that what we will do is we will write this current source in parallel with resistance as 4 into Ix into 2, that is voltage source in series with the resistance. Here plus and minus here, and V is equal to 2Ix into 2 is equal to 4X. I have represented here, and series 2 ohms here. Now 2 in series here. So what we will do is we will write as a combination 4. So voltage source in series with 4 ohms. I is equal to V by R. I can write again here. So I can convert into this 4 Ix voltage source in series with the 4 ohm resistance can be represented as a current source of Ix value. Why? Because I is equal to V by R now. That is, here we have Ix and 4. 4 and 4 parallel with, which will give 2. Again, after writing this of 2 ohms in parallel with Ix, I can represent again in terms of voltage source in series of resistance, so that we can get the answer as 10 amps here. Next, we'll discuss superposition theorem. In any linear active bilateral network consisting of number of voltage sources, current sources, resistance, etc., different, the effect produced in any element when all the sources act at a time is equal to the sum of the effect in the same element when each source is considered independently here. That is, while applying superposition theorem, we consider only one source at a time and other sources are represented inactive here. Okay, so important note here is dependent sources cannot made inactive here. So what is the meaning of inactive here is making the source as a dead. That means if you have a voltage source, we'll make it short circuit. If you have a current source, we'll make it open circuit here. So let's solve a question which I asked in GATE 2003. Friends, here we need to find the VPQ, that's the voltage across the points P and Q. Here we need to find. So in this case, number of sources are 2. That means here 10 volts and 2 amps. So we have two subcircuits or two cases. In first case, what you will choose is 2 amps is an active source and 10 volts is an inactive. That means we will represent with a short circuit. So here 10 volts I represent with a short circuit here like this, and between PQ we have 2 ohms and 4 ohm resistance and 8 ohm and 6 ohm resistance, 2 ohms. So when this short circuited, that means 4 into 6 is going to be parallel to 8 into 2 is going to be parallel. Okay, when you perform the parallel operation of these two, then we will have, so 4 into 6 by 4 plus 6, 2 into 8 by, divided by 8 plus 2, so 1.6, 2.18. So we will get PQ here, and current is flowing from Q to P here, and this equivalent is going to be 4. So 4 into 2 is nothing but 8. Okay, so that's what I have written here, VPQ. But we want VPQ here. So for the first case, I will write dash here. So VPQ dash and then VQP dash here. So VQP dash is equal to 8 volts. Then V dash PQ is equal to minus 8 volts. So opposite polarity. So next case 2. So 10 volts is active and 2 amps is inactive. So 2 amps is inactive means I am going to make the 2 amp source inactive. So we are going to use we are going to open circuit the 2 amp source. So this is the actual diagram, and we have opened this circuit here. So 2 amp source is going to be inactive. Now, so if you just observe here, I want to know P double dash and Q double dash here. Okay, so if you redraw the circuit like this, then VP double dash and VQ double dash we need to find. So by using the voltage division rule, VP double dash is equal to 8 volts. We will get it. That is 8 ohms into total voltage divided by 8 plus 2. And similarly here VQ dash is equal to 6 ohms into 10 volts divided by 6 plus 4. So from this we will get it. So what is a V double dash PQ? That is nothing but VP minus VQ. So what is VP and VQ value here? We got that is 8 volts and 6 volts. So from this we got second case. By superposition theorem, we will sum up all the responses of sources individually. So VPQ dash plus VPQ double dash is equal to VPQ. This is equal to minus 6 volts. Why? Because here 2 volts and minus 8 volts. So when combined together, we will get minus 6 volts. Right. Next. So find the power delivered by 2 amp source. So this is a question which was solved in node and mesh analysis, and we have solved it, and we have got the power also. So here in this case we are going to solve this same problem by using our superposition theorem. So power is nothing but it's a product of voltage into current, and here we know that current. Why? Because current, what is the power delivered by 2 amps? Okay, so we know the current, we need to find the voltage. So here our main target is find the Vx here. Okay, so here directly, so important notice, power is a non-linear parameter which cannot be found by superposition theorem directly here. So as what we have done previously, so P is not equal to P1 plus P2. Okay, because power is a non-linear element. So in this case we have 3 sources. I will choose the first 10 volts is active, and the remaining 2 sources, that is 5 volts and 2 amps, are going to be inactive. So 5 volts inactive means short circuit, 2 amps inactive means open circuit. Okay, so here what I have done, 2 amps is going to be inactive, open circuited here, and 5 volts is going to be short circuited here. So these are equivalent representation here. Here if you observe here, so the plus Vx is there. So plus Vx is nearer to minus of 10 volts. So plus Vx is minus of 10 volts here. So from this, if you observe here, 10 volts 10 volts in parallel with the 2, and 10 volts, it's a 10 volts in parallel with the combination of 1 ohm and 1 ohm in series. So voltage distribution, if you apply here we have 5 volts, and here we have 5 volts. So by observing this, Vx dash is equal to first case is minus 5 volts here from this. Okay, otherwise we can also apply voltage division rule also here. Next case 2. So 2 amps is active and 5, 10 volts is inactive. That means here in this case, so 2 volts is active, so 5 and 10 I'm going to be short circuited here. So this shorted here. So when you short this time, so 2 ohms is not going to be have any significance here. Okay, why? Because it's shorted now. Next, so that the current will distribute, so 2 amps is going to be equally distributed among 1 ohm and 1 ohm, and Vx is going to be, so plus minus here, so current is flowing 1 volt, so Vx is nothing but 1 volt here, so V double dash is equal to 1 volts because of case 2. And next, third case, so 5 volts active and 10 comma 5 amps is inactive. Okay, this is a 5 volts, and here we have plus Vx. So by again voltage division rule, we get 2.5 volts and 2.5 volts here, so Vx is equal to 2.5. So by superposition theorem, add all the responses, then Vx is going to be Vx dash plus Vx double dash plus Vx double dash. So from this we get minus 1.5 volts. Friends, power delivered by 2 amps is nothing but power voltage across the element into the current. So here we have minus 1.5 into 2, this is what minus 3 watts. So this is the same answer what we got by solving the same problem, node and mesh analysis, in my previous lectures. Okay, and here, so this problem also we have solved in my last node and mesh analysis session. So find the power delivered by 5 volt source. At that time we got the answer as a minus 275 divided by 8 watts here. Okay, so try this problem, you will get the same answer. If you have any problem or difficulty, then please comment, then we will try to solve your problem. Next case, next here, the power lost in R when V acts alone 9 watts and when I alone acts is 4 watts. What is the total power lost in R when both acts together? So this kind of problems you may expect in Genco and Transco and other PSUs. So let's, when V acts alone, what is the power dissipated? 9 watts here. So P is equal to V1 square by R. We can write R, I can write I1 square into R1. So I1 is equal to just I1 square is equal to what you will get. So from this, so here I1 square is not there. So here this is I1 only. So I1 is equal to, from this, I1 is square root of P1 divided by square root of R1. So what is the P1 value? Already they have mentioned that 9 watts. Okay, so from 9 watts we will get, so square root of 9 divided by square root of R1, 3 by R1 here. Similarly, I when I acts alone, I2 square is equal to square root of, here also we have mistaken. So I2 is nothing but square root of P2 divided by R2, that is what 2 divided by square root of R2. Why? Because P2 is nothing but 4 watts here. When resistance is remain same, so R1 is equal to R2 is equal to R. When both the cases are acting together, so PT total power is equal to I1 square plus R minus I2 square into R. So this can be written as, if I send R inside of these brackets, then I1 into square root of R plus I2 into square root of R whole square, so plus or minus here. So when these two are plus or minus means, so when the currents are I1 and I2 are same direction, then I1 plus I2 whole square together. When they are opposite direction, I1 minus I2 here. So from this, so 2 plus or minus 3 whole square. So when I1 and I2 are same directions, so 2 plus 3 whole square, that is about 25 watts. When they are opposite directions, 2 minus 3 whole square is equal to 1 watt. So this is the solution here. And we next discuss the Thevenin's theorem. So Thevenin's theorem, in any linear bilateral active network consisting of any number of energy sources, resistors, etc., with open output target terminal defined, can be considered into a simple network consisting of voltage source in series with the resistance. That means any big network consisting of number of voltage sources and number of resistances can be represented as a single voltage source in series with the resistance at open the output target terminals here. So we will discuss what is that open output target terminals here, and let's see the Norton's theorem. Why? Because they are actually dual together. In any linear bilateral active network consisting of energy sources, resistors, etc., with a short output target terminal can be considered into a simple network of current source in parallel with the resistance here. So any network can be represented by its current source in parallel with the resistance. Actually, if you observe here, they are actually source transformable here. That means voltage source in series with the resistance can be represented as a current source in parallel with the resistance here. Okay. Next, we will discuss some problems here. So in this case, Thevenin's theorem. So we may expect three cases, different cases here. So first case is problems with only independent sources. That means we have only independent sources here. So here find Vx by Thevenin's theorem and Norton's theorem here. And we have solved this same problem in our node and mesh analysis concept. And here we are going to solve the same problem, and we will get the same answers or not. So first, in Thevenin's theorem we need to find VTH and RTH. So first we will find VTH here. So in VTH, what we will do is, so first we will open the output target terminals. So here we need to find Vx. At that point, I will open it first. So I will open it and I will name it as plus minus VTH here as like this. Okay friends. Next. So after doing this, we need to find what is VTH here. So in order to find VTH, we can also use different techniques, node mesh analysis, or you can use KVL, ACL, or you can use source transformation technique, or any other techniques you can use. So here, what we have chosen is, you need to find VTH here. And first here, the current source is current flowing like this through a 10 volt source. As we know that when a voltage source and a current source both are in series, this equivalent circuit will be having a current source only. So the 5 amps is the current flowing like this in this case here, up to this point. Okay, so after this, the 5 amps is going to be equal distributed. So 2 plus 1 is 3 and 3 here. So 3 means parallel. Okay, so they are equal distributed. That is 5 amps is the current is going to be equal distributed here. So 2.5, 2.5. And so by applying here KVL, so minus 10 plus 2 into 2.5 plus VTH. So we'll get VTH is 5 volts. And here next, in order to find the RTH, we make all the independent sources inactive. That means if there is a voltage source, short it. If there is a current source, open it. So here what we have done is a current source here. I have opened it here, and here 10 volts current source, voltage source is there. I have short it here. Okay. So if you find the RTH between these 2 points, so 3 ohms and 1 ohm are in series here. So 4 into 4 in parallel with the 2 here. So we'll get this value. And after finding VTH and RTH, I will draw the equivalent circuit of it. Okay, that means this circuit can be represented by its voltage source, equivalent voltage source, and equivalent resistances here. Now here we need to find Vx. So Vx across 2 ohms. Okay, so Vx across 2 ohms here. So from this network, by voltage division rule, what we can get? So Vx is equal to 5 into 2 divided by 2 plus 4 by 3, we will get 3 volts here. And similarly, now we'll solve the same problem with Norton's theorem. So in Norton's theorem, we need to find IN value. So Rn is equal to RTH is equal to 4 by 3. So for both the cases, RTH or Rn value both are same. Next IN case. So next IN case, what we are doing here is, we are going to make the output target terminals are short circuited here like this. Okay. So when a short like this, then here by applying KCL here, so current 5 amps is entering here, and here IN is entering. So 5 plus IN is entering here like this. So this is the process here. Up to this point, 5 plus IN is current entering here, and 5 amps is the current leaving here. Okay. So why 5 amps current leaving here? It means if you apply KVL here, minus 10 plus 2 into I is equal to 0, that means I is equal to 5 amps here. That means in this branch, 5 amps is the current flowing, and the remaining IN is going to be flowing like this. Okay. So by KVL at this particular point at loop, we get, so minus 5 into 2 minus, that is minus 10 IN into 3 plus, again come back here, and IN minus 5 into 1. So by solving this, we will get IN as 5 by 15 by 4. Now we will draw the equivalent circuit, a current source in parallel with the equivalent resistance Rn, and here the target terminals are plus or minus Vx, which is across 2 ohms. So now Vx can be found by current division rule. So current division rule, we will get the Ix value. So by Ix value, Ix, so Ix into 2 is nothing but voltage. So directly I have done here, Vx is equal to this value, 3 volts. And this is the same problem which we discussed in node and mesh analysis. So solve this problem by Thevenin's and Norton's theorem. So let's continue discussion in case 2, that is Thevenin's theorem. So problems with dependent and independent sources. That means here in this one we have both the combination of dependent sources and independent sources here. So in this case, we can't suppress the dependent sources, so we can't find the RTH or Rn directly as earlier. So but from Ohm's law, what we will do is, RTH can be written found from, so V open circuit divided by ISC or VTH by IN. Okay, that means so in order to find the RTH, you have to use both the Thevenin's theorem as well as Norton's theorem. So let's solve a problem which are asked in GATE 2009. So find RTH and VTH here. So this is the problem which will have both the independent sources as well as dependent sources here. So in order to solve this problem, I need to find VTH and IN, that is Thevenin's equivalent and Norton's equivalent here. Okay, so first I will find VTH here. So here by source transformation, voltage source in series with resistance can be represented as a current source in parallel with the resistance, Okay, so that, so 5 by 2 kilo ohms is nothing but 2.5 milliamps in parallel with the 2 kilo ohms and 2 kilo ohms. And here we have 3 VAB and here VAB. So here at the open target terminals we have VTH is nothing but VAB here in this case. Next case, what I have done, so after 2 kilo ohms and 2 kilo ohms are parallel, it's equivalent to 1 kilo ohm, and I have converted, so 2.5 milliamps in parallel with 1 kilo ohm as like this. So that is voltage source in series with the resistance, and here we have 3 VAB and plus or minus VAB here. So VAB is nothing but, if I assume that mesh current is I1, so I1 into 1 kilo ohm is nothing but VAB here. So by applying KVL in this loop, so minus 2.5 plus 1 kilo ohm into I1 plus 3 VAB. So what is a VAB? Is nothing but I1 into 1 kilo ohm. So 3 into I1 into 1 kilo ohm plus 1 kilo ohm into I1 is equal to 0. So by solving this, we will get I1 as 0.5 milliamps. Next, VAB is nothing but I1. So 0.5 milliamps into kilo ohms. This is what open V, that is 0.5 volts. So with this, VTH is found. And next, what we need to find? We need to find IN. That is IN. So here at this output target terminal, we have to short circuit in order to find the IN value. So ISC. So once I short this, what will happen? So 1 kilo ohm in parallel with a short circuit. So it has no effect. That means it's a short circuit here. Next, VAB here. So VAB is shorted means VAB is 0. So once VAB is 0, so 3 into VAB is 0. So voltage source is short circuited means 0 means it is short circuited here. Next, here it will come. Okay, the short circuit. Again, the short circuit across 2 kilo ohm is going to be again a short circuit. So here we are going to find ISC value. So ISC is nothing but, so 5 divided by 2 kilo ohm is equal to 2.5 milliamps. So we found VTH value and ITH value. Next step is RTH. So RTH is nothing but VTH divided by ISC, nothing but 0.5 divided by 2.5 milliamps is equal to 0.2 kilo ohms. And next here, so find the Norton's and Thevenin's equivalent between RL here. So here we need to find the RL here. Okay, so friends, if you solve this problem by using the Thevenin's and Norton's theorem which we discussed earlier, you will get the options like this. Okay, so try this and we'll move to the next case 3 here. So circuits with only dependent sources. In this type of problems, only passive elements are present but not active elements. So we can't find VTH, car, IN, but only RTH. So if you can't find VTH and IN, then how can you find this RTH? So here, in order to solve this, we are going to assume, so VT and IT are the test voltage and test current respectively, are externally applied to the source. That means in this case we are not going to find RTH, VTH and IN. Sorry, VTH and IN we cannot find, only RTH we can find here. So let's solve a problem here. So which is asked in GES 2012 here. So here friends, they have asked the problem like this, and we need to find what is the value of RTH. So RTH is nothing but, so RTH or RN is equal to VT by RT. Suppose if I give test voltage as a 1 volt, then RTH is equal to 1 by IT here. So I have simplified the circuit. So 9 kilo ohms and 1 kilo ohm are series. It will combine 10 kilo ohms, and IB is flowing downwards like this, and we have 100 ohms, and here we have a current source of 99 IB here. Okay. Next here, friends, if you observe here, if I am applied here a test voltage of 1 volt, so plus minus here, and this is going to be IT. And if you observe here, IB is going to be opposite direction here. So here we have 1 volt and IB and resistance. So I is nothing but V by R. So IB is nothing but V is nothing but 1 volt divided by 10 kilo ohms. And here actually this is moving in upward direction. So here we have minus sign. Okay, so minus sign means we will get IB as minus 0.1 milliamps. And what about I100? That is current flowing in 100 ohms. So we have voltage as voltage of 1 volt. So I is equal to V by R 1 by 100. This is a value. Okay, so by applying KCL here, so incoming currents are considered as a negative sign and outgoing currents are assigned with positive sign. So incoming currents minus IB and minus 99 AB is equivalent to 100 AB. So minus 100 AB, and IT is entering minus IT plus I100. Okay, by substituting IB value in this case, you will get IT is equal to 0.02 amps here, and RTH RN is equal to 1 by IT. So this is nothing but 50 ohms here. So next we'll solve maximum power transfer theorem. which states that in any linear active bilateral network consisting of number of energy sources with their internal resistances, maximum power is transferred to the load when the load resistance is equal to its equivalent resistance as seen by the load into the supply circuit. So to explain the maximum power transfer theorem, let us consider a circuit in which we have Vs1 is a voltage source, Rs is a source resistance, and RL is a load resistance here. So here friends, from this IL is equal to Vs by Rs plus RL we can write here, and power losses in resistance is equal to IL square into RL. So IL is nothing but Vs by Rs plus RL whole square. So by substituting this we can get. So to get the maximum power transfer to the load, we will use maximum or minimum condition. So from that we'll use differentiation. So dPL by dRL. So here RL is a variable here, is equal to 0. So here the useful formula is d by dt of u by v is equal to v into du by dt minus u into dv by dt divided by v square, and which is equal to made equal to 0 here. So from this d by drl of what's the PL? So vs square into RL divided by Rs plus RL whole square here. So by substituting and differentiating and equating to 0, you will get that RL is equal to Rs. That means when you will have load resistance equal to source resistance, you will get the maximum power transfer to the load. So now, so PL is nothing but, so this is going to be Pmax. So PL at source resistance equal to load resistance, it is going to be give maximum output. This is equal to 4 VTH VTH square divided by 4 RL here, right? So here in this state, so VTH square divided by 4 RL here. Next, that is maximum power is to the load. So maximum power transfer to the load is 4 VT, not again here. So sorry, here we have mistaken. So it is going to be VTH square divided by 4 RL here. Okay. So the power delivered by the source is equal to, that means, so source is going to deliver the power to the Rs and RL here. Okay. So IL square into RL plus IL square into Rs. This is equivalent to, when RL is equal to Rs, we will get it as, so 2 VTH square divided by 4 RL. So this is going to be VTH squared by 2 RL here. So this is power delivered by the source. Efficiency is equal to output divided by input power. That is equal to, so output is going to be, so 4, VTH square divided by 4 RL into, next this is divided by, so VTH square divided by 2 RL. So we'll get 50% of the maximum efficiency here. So by maximum power transfer, we can transfer only 50% of the input power to the load, and the remaining 50% is going to be lost in resistance. Okay, so let's solve some problems here. So before we discuss the problems, let's discuss very important analysis, AC analysis of maximum power transfer theorem, which is very important for GENCO and TRANSCO and APSPDCL, okay, and PSUs. So in this case, so first what we will do is we will take Rs and Jxs is the inductance, that is a total impedance here, and here we have impedance here. Okay, so IL is a current vector. IL is equal to Vs is a vector divided by Rs plus RL plus Jxs plus XL. So these are in vector form. If you want to get the magnitude here, so IL bar is equal to, so Vs bar divided by magnitude of Rs plus RL plus Jxl plus XS. Okay, so magnitude is going to Vs here divided by square root of Rs plus RL whole square plus XL plus XS whole square, and P is equal to I square RL here. So from this I square is Vs square divided by this square into RL here. And here first case is when RL is the only variable. So whenever there is a variable, we will differentiate the power losses with that variable, and we will find the maximum condition when it is going to be occur. So dou PL by dou RL is equal to what we are doing. So dou by dou RL of PL, this value is equal to 0. So by differentiating, we will get that, so RL is equal to square root of Rs square plus XL plus X square. So what is the conclusion here? When here in the load, the only variable is RL here and XL remain constant. So at that time, so RL is equal to Rs square plus XL plus XS whole square. So that's the conclusion. Okay, so for maximum power transfer, this is the condition. Next case is when XL is variable and RL is constant. So in this case here, again this case, when XL is variable, RL is constant. Okay, so in this case, so dou PL by dou XL is equal to 0, and we can get that XL is equal to XS. That is XL is equal to minus XS. This is a condition. So from the two conditions, what we will get is, we will combine these two conditions if RL and XL both are varied. So here friends, when the first RL is varied means RL is equal to RS plus J XL plus XL whole square. We get that. And next, when XL only is variable, so XL is equal to minus XS. When these two are combined means you get, so this is the condition. So when these two are combined means we will use these two conditions. When these two are conditions used means we will get RL is equal to RS, XL is equal to XS. That implies ZL is the load impedance is equal to complex conjugate of source impedance. So this is very, very important. I will repeat again here. When RL and XL both are varied, then ZL is a complex conjugate of the source. Okay. And next, so when ZL is equal to Z is complex conjugate, then what is the power maximum? So power maximum will get is Vs square divided by 4RL here. Okay. Next case, special case here. When XS is equal to 0 and RL is variable, just substitute this equation into this equation. That's it. When what is the condition? XS is equal to 0, so RL is variable here. So here XS is 0. So that means RL is equal to square root of RS square plus XL square. That's it. That's what we got here. Right? Next, so a problem on this here. So find the maximum power transfer to the load RL here. So P max is equal to VTH square divided by 4 RTH. Right? So here, check for the bridge is balanced or not. Suppose, let's see here if the bridge is balanced or not. So if yes means no power flow here. So we'll see that case in the next problem. So 1 into 4 is equal to 4. 1 into 4 is not equal to 3 into 2. So this bridge is not balanced here. Next, we need to get P max is equal to VTH square by 4 RTH. Okay, so we'll redraw the circuit like this. And here we need to find VTH between A and B here. So 20 amps is the current flowing here. So by using the current division rule, I get I1 value as 12 amps and I2 is a 8 amps. So I1 is the current flowing inside this in this branch, and 8 amps is current flowing in this branch here. So by applying KVL here, so minus 3 into I1 plus 4 to VTH plus 4 I2. By substituting this equation, we get VTH as 4 volts. Okay. Next, I want to know RTH. So what is RTH? So RTH means current source should be open circuited. So RTH is going to be this equivalent. That means in between these two we are going to find. So 1 and 2 are in series, 3 and 4 are in series. We will get 7 parallel 3 is nothing but 2.1. So P max is equal to VTH square divided by 4 into RTH. We will get 2H. Next here. So what is the maximum power transfer to the load resistance here? So check whether the bridge is balanced or not. So 8 into 2, 16. 4 into 4, 16. So bridge is balanced here. When the bridge is balanced here, maximum power transfer is not possible. So maximum power transfer is not possible in this case here. So come on friends, next problem. So find the maximum power transfer between the point A and B here. So this is a simple circuit in which we have dependent sources and independent sources here. So first here we have a dependent voltage source here, and it depends upon I0 value. So first we will find I0 value by using voltage division rule here. So I is nothing but 40 divided by, so 2 plus combination is 2k, that is 4k here, into 3k by 3k, 9k here, 6k by divided by 9k. Okay, so we get 5 milliamps here. Next, KVL in this equation, we'll get minus 50 into I0 plus 10 into I2 plus 10 into I2 is equal to 0. And from solving this, I2 is equal to 25 by 2 milliamps. And what is a VAB? So VAB is nothing but 10 into I2. Okay, so that 25 by 2 into milliamps into 10. So we get 250 millivolts here. And we need to find RTH. So when we want to find the RTH, what we have to do? So we have to find open circuit by ISC. Why? Because we cannot directly apply, because we have dependent sources. So RTH is equal to VOC by ISC. So VOC is nothing but a VTH by IN. So already we know what is VTH, 250 divided by 2 millivolts, and IN I to find. So in order to find IN, I will short circuit these 2 points A, B here, so that what you will get, so minus 50 into I0 plus 10 into IN is equal to 0. So this is because IN, here you have short circuit, so 10 ohms is not going to have any role here. So this is going to be by 50 minus 50, so plus 50 IN plus 10 into IN is going to be 0. Okay, so from this IN is got as 0.025 amps. Next case is RTH. So RTH is nothing but 125 into 10 power 3 divided by 0.025 value. Okay, and you will get P max is equal to VT square divided by 4 RTH, and this is the answer. And next problem is, so for what value of R maximum power transfer from the circuit A to B is going to be transferred. So for maximum power transfer, the voltage is equally divided across the load and the source. So here if we have 20 volts here, so here we have 10 volts and here we have 10 volts here. So by using this by this technique, the load is equally distributed across the load. So that means here we have 10 volts. Okay, so 10 volts is going to appear here. So 10, so by applying nodal analysis, 10 minus 20 divided by 10 plus 10 by 20 plus 10 minus 5 by R. So from this R is equal to 10 ohms. And we will next move to the next theorem, so reciprocity theorem. Okay, which says that in any linear passive bilateral network excited with only a single independent source, okay, not dependent sources, it's a single independent source, the ratio of response to the excitation remains constant when if the positions of the source and the load are interchanged here. That means, suppose let's consider a network and this is a network here. So in this case, the voltage is a force and current is a response. So it's the input excitation and this is a response here. So when you interchange this, that means here you have here you have response and here you have excitation, and when these two are changed here, then the ratio of response to the excitation is going to be remain same in both the cases. So let's solve this problem here to understand this. Okay, so verify the reciprocity theorem for the below circuit and find the value of I. So while writing the reciprocity network, reciprocating network of a given network, ideal voltage source are connected in series to the targeted branch and current source in parallel respectively. So in this case here, so here we have 10 volts the source and here we have the resistance here. Okay, so these two places are going to be very, very crucial here. So what we will do is, first I will take this 10 volts as it is and I will find the value of I. Okay, so by using nodal analysis I will find the value of I. So V1 minus 10 divided by 7, V1 by 7 and V1 by 6 is equal to 0. So from this V1 I got, and also, so this is, I mean I1 is equal to V1 by 2, I got this value. Okay, so the ratio of excitation, the ratio of response, so I by V, so this is going to be, I is nothing but 10 by 15 by 17 divided by response, I mean excitation is 1 by 10. So we get this value. So next case is, what I am doing is, so in this case I will take the voltage source in series with the target terminal here. That means I will place voltage in series with this here and I will take I value here. Okay, so this is here. So here I will choose I value. So I is going to be flown in which branch? 2 ohms branch. Okay, so here, and by writing this equation I will write, so V1 by 7 plus V1 minus 10 by 2 and plus V1 by 6 here. So by using this condition I will get the value of V1 value. Okay, so here I1 is going to be found in this here at this point. Okay, so I1 is nothing but, we got, so 105 divided by 17 by 7 here. So here we got the response. Okay, so here we, in this case is a 4 plus 3 7 ohms. So we got the response I here. So from this, the ratio of output to input, that is response to the excitation, we get 15 by 170. So hence reciprocity theorem is verified here. And next, verify the reciprocity theorem in the next problem. So here we have a current source of 10 by 7 and 1 ohm, 7 ohms, 6 ohms and 2 ohms here. So here's the output is V0. So V0 directly can be found by using any method. So V0 is, I got is 2.068 volts here. The ratio of output response to input excitation is, so 2.068 is the response, and input is going to be 10 by 7. I will get as a 1.44. Next case, what I have to do is, I have to change, that means current source is to be connected across this and V0 is to be connected in series with this here. So I will redraw the circuit, observe here, and here we have source and here we have response. And next I will use the same formula which we have discussed earlier in my previous sessions So from this I got the 2.068 volts here. The ratio of output response to the input response is same. That means hence reciprocity theorem is verified here. Okay, and next, and third problem, use a data in figure A to find in figure B. So here in this, friends, we have 5 volts. When we have 5 volts, we have response of 2 amps. When we have 10 volts and 30 volts here. So for Vs is equal to 5 volt source, we have IS supply current as 4 amps and load current as 2 amps. So from linearity, what we can get, so if the source is 10 volts, suppose this is a 10 volt source, then we have IS is equal to 8 double and IL is going to be double. Why? Because voltage is double. Suppose if the Vs is equal to 30 volts, then I is equal to 24 amps and IL is equal to 12 amps. So next I will write out the circuit here. So here I have 10 volts source which will supply current of 8 amps, and here I have 30 volts source which will supply the load current of 12 amps. So these two are in this direction. So what is the actual I value? So I value is from 10 to another network. So from this is the 10 to network here. That means the current flowing is going to be minus 4 amps in this case here. Okay, and next, intelligence theorem. In intelligence theorem, it states which is a verification of a law of conservation of energy here. So this theorem states that the algebraic sum of the powers in a network or circuit is going to be 0. Okay, so verify the intelligence theorem here. So this is a problem which we have discussed earlier. Okay, in reciprocity theorem. So now what we will do is we will find the value of IS here. So IS is going to be, so 10 voltage divided by total impedance, we will get 20 by 17 here. Okay, that's 1.736 amps. IS square is equal to, that is supply square is equal to 1.84 amps here. So total input power is nothing but the product of IS into 10. That means IS is 20 by 7 into 10, so 200 by 17. And next here, so I 2 ohms. So this is in this 2 ohm branch, how much current is flowing? Okay, so I 2 ohm is nothing but 20 into 17 divided by current division rule. So 6 by 8 is equal to this value. So similarly, by applying current division rule in this branch, I will find 0.294 amps here. Next, so and here, so I'm going to find each and every element power here. So P power of 3 ohms. So I square, that is 20 by 17 I square into how much? 3, and P4. So this is nothing but, so 20 by 17 is the current flowing, I square into R, that is 4. And next in this branch, 2 ohms branch, how much current is flowing? So I 2 ohms. So I 2 ohm is nothing but 0.882 x square. So 0.8 is equal to 2, that is 1.55 watts. So similarly P1. So how much in 1 ohm flowing is 0.294 square into 1. Okay, and similarly we get P5 ohms and P10 volts. So algebraic sum of the currents powers is going to be 0. That means, so here we assume that so power absorbed in element is positive and power delivered is going to be negative. Okay, so power delivering is only 10 volts and remaining are absorbing. Okay, so if you sum up all these things, then you will get 0 watts. So approximately, why? Because so this is 0.0067 is because of the calculations. Okay, next, Millman's theorem. So Millman's theorem is also called as a parallel generator theorem. So which states that a number of voltage sources in series with the resistances connected in parallel can be represented as a single voltage source in series with the resistance here. So here V dash is equal to V dash, that is equivalent value of V dash. V dash is equal to sigma I is equal to 1 to n Vi by Ra divided by sigma I is equal to 1 to n divided by 1 by Ra here. Okay, so this is equal to, so sigma I is equal to 1 to n Vi into Gi divided by sigma I is equal to 1 to n Vi into Gi here. So this is for voltage V dash, and next R dash is going to be 1 by sigma I is equal to 1 to n 1 by Ra here. So from this it can be written as 1 by sigma I is equal to 1 Gi here. So in order to understand this problem concept theorems here, let's find a problem here. So which was asked in GATE 98. So find VAB and RAB here. That means, so this is a network which can be represented as like this, and find VAB and RAB. So from the above formulas, so VAB is equal to sigma I is equal to 1 Vi by Ra divided by sigma I is equal to 1 by Ra here. Okay, remember this, friends. So Vi is nothing but 5 and series resistance is 4 and plus, so and 10 ohm resistance is there. Okay, so 10 volts resistance in series with 6 ohms divided by 1 by 6 plus 1 by 4, we will get 7 volts here. So VAB we got 7 volts, and RAB we can get is, we can get 2.4 ohms here. Okay, so this is the problem. Next, Compensation theorem. So compensation theorem is useful to calculate the steady state errors in measuring instruments of analog instruments here. So this theorem allows us to calculate the correct values of electrical parameters such as voltage and current when they are subjected to parametric variations within the circuit here. So the parametric variations due to temperature or aging effect or interconnection of some other elements, some other components here. So in network 1 we have current flowing is I and resistance is R here. But when we connect some other elements such as ammeter here, when you connect ammeter here, what will happen? Ammeter will have resistance. So it will add the resistance to this existing network so that the current value is going to be changes I dash here. Okay. So now what we will do is we will going to compensate this drop here. Okay. So by using compensate network without any sources here. Okay. So important is without any sources we are going to take here. So VC is nothing but compensated voltage, which is nothing but the current flowing already is I into delta R, that is change in resistance. Okay, after that we see is delta R into I, and here delta R is the resistance and R is the actual resistance. Okay, and the compensation current IC is equal to I is the first case and I dash is the second case here. So to understand this concept, let's solve a problem here. So find the change in current introduced by the ammeter with an internal resistance of 0.15 ohms while assuming that the current in 6 ohms resistance branch. Also determine the steady state error introducing the meter. So first here we have a network. In this network 6 ohms here and I is a normal actual current flowing here. So when we are connecting ammeter here, ammeter having 0.15 resistance, that is delta R value. First we will find I value. So by using the current division rule, we will find I is nothing but 2.5 amps. So next condition is calculate the compensated voltage. So VC is nothing but I into delta R. So I is nothing but 2.5, delta R is nothing but 0.15. Okay, so 0.15 means this will get this value. So VC is nothing but 0.735 volts. Next case, step 3. So compensate network. So what we will do, we will remove all the sources. That means this source is short circuited here, and I will inject VC voltage delta R and R as we discussed in theorem here. So from this IC we can get, so IC is nothing but total voltage divided by total resistance. We will get 0.051 amps here. Now the steady state error in percentage is going to be IC divided by total current I. So I is not the first current here. I is nothing but this is the I value. So 2.5. Okay. So IC is nothing but I. So 0.05 divided by 2.5. We will get 2.04 is the error here. And the last theorem of the session is substitution theorem. So in any linear active bilateral network consisting of number of energy sources, passive elements, etc., any passive element can be substituted in terms of its equivalent voltage or current for the further analysis of the network without disturbing the rest of the network, provided the power dissipated by the passive element and its equivalently substituted source is same. So to understand the substitution theorem, let's observe an example here. So normally, so if you observe this, we will see that it's a bridge. Okay, for substitution theorem, we will replace 5 volt source with a resistance R here. That means the first is find IS if the bridge is balanced. That's the question. So if the bridge is balanced, means what will be the resistance here? So 1 kilo into 1 kilo is equal to 1 kilo into here 1 kilo. So if here is 1 kilo, then we will find, then we can say that find that the bridge is balanced here. Okay. So what I have done is I have replaced this 5 volt source with a resistance here, and as we know that 5 volt source is nothing but I into R. So already we know R is value. So what is R is nothing but 1 kilo. So I is nothing but 5 divided by 1 kilo. That's it, 5 milliamps. Okay, if the 5 kilo amps, 5 milliamps is the current flowing in this branch here. If you observe here, so 1 kilo, 1 kilo, 1 kilo and 1 kilo. That means they are parallel and have equal resistances. So the current will flow equally here. So that means if there is a 5 milliamps and here also 5 milliamps, so total supply is 10 milliamps here. And the last problem in this session. So using the substitution theorem, find the value of VA for which the maximum power is to be transferred to the load. So here maximum power transfer to the load is the condition, and here VA we need to find. So first what we will do is we will replace the VA with a resistance R here like this. VA is nothing but R into I, and in order to transfer the maximum power transfer from the source to load, this load resistance should be equal to source resistance. Okay, so that we will combine, so 20 in parallel with 5 plus R is equal to 10 ohms. So because source resistance is 10 ohms now, so from this we will get R is equal to 15 ohms here. So now IS is equal to how much? So IS is the current we need to find. So 5 plus 15, 20. So 20 in parallel 10. So 10 plus 10, 20. So I is nothing but total current IS is equal to 20 by 20, that is I amps, that is 1 amps here. And now I is equal to, so in this case I is nothing but 0.5 amps. Okay, so now VA is equal to R, that is how much, 15 into 0.5 is equal to 7.5 amps. So thank you friends. If you have any doubts in this session, you can comment, and if you want any other subject videos, you can comment here. And especially for APGenco and APTransco people, those who can't understand English very well, that means they want in regional language, they can also comment, so that I can give my lectures in Telugu also. Thank you friends, thank you for watching, have a nice day.